All right. I hope everyone ready. Hi, everyone. Welcome to the EURASIP webinar. So first of all, just to inform you all that this talk is recorded. So you are aware with that. Today, we are very grateful to host Professor Michael Unser, who is also our EURASIP fellow. So Professor Michael is full professor with EPSL School of Engineering and the education director. Sorry, someone gonna mute it. So if you're not yet mute yourself, can you please? Thank you. Professor Michael is also the academic director of the EPSL Center for Imaging. So his primary research area are signal processing, biomedical imaging, and applied functional analysis. So he is internationally recognized for his research contributions to sampling theory, wavelets, and the use of the SPLI for the image processing and computational bioimaging. So he has published more than 400 journal papers on those topics. So in today's webinar, Professor Michael will present a principal framework on universal and efficient learning of convex pliers for inverse problem. So Michael, if you're ready, over to you, please.
Okay, so thank you very much for the introduction and also EURASIP for the invitation. Actually, I've been a member of EURASIP maybe 40 years now. Okay, so what I want to tell you is about a way of actually learning priors for solving inverse problems, and you will see there's a nice connection also with compressed sensing, and so that will put things allow us also to make efficient implementations. Okay, so what is the context? So it's really computation.
Sorry, Michael, would you like to share your screen?
Oh, I don't share?
Yeah, not yet.
Oh, okay, because I thought I was. Okay, so.
Actually, I was saying it was okay for me.
So is it okay
Yeah,
like
it was
this?
being shared.
Yes.
Yeah.
Yes, it's perfect.
Okay, so the context is computational imaging, so reconstruction of images, and maybe just to describe the problem. So here we want to reconstruct, let's say, a slice of the body. We have observations through an X-ray scanner, which will give us measurements which are radon samples of the radon transform, so projections. And this measurement process, so it's modeled here by this matrix H, because I mean this is a linear measurement process, and unfortunately we also have measurement noise, and so here the problem really is to reconstruct S, so which is our unknown signal from the noisy measurement Y, knowing the physics which is modeled by this H. And so there are like two dominant paradigms now in the field. And so the goal here is really to go from those measurements, I recall they are Y here, back to this signal. And so in the sort of classical framework, we have usually formulated that as a convex optimization problem. So that's what we call the variation paradigm. And so here what we need to minimize is a cost functional with a term here that kind of promotes solution that explain the data well, but because often those problems are ill-posed or because of the noise, we also impose some regularization, usually using some kind of operator that acts on the data and minimizing some norm. It can be a 1 or a 2 norm, and I'll give you a little more indication. Okay, and then there's the deep learning paradigm. So where, let's say it's a more pragmatic approach here, we want to train, let's say, a neural network so that if we enter the measurements Y, so the output of this neural network would give us the desired signal. And so this can only be achieved, of course, if you have representative data of measurements and corresponding reconstruction, of course, that you need to have done with some classical algorithm. So the variational paradigm, so this is really an old story, so it's classic signal processing or inverse problems, and it's also very much, you know, in the center of, let's say, second generation image reconstruction methods like compressed sensing. And so if we really go very classic, and so classic goes with 20th century and the 2 norm, and in this case, we are trying to solve this problem. So it's always the same problem, but now with a regularization that is a quadratic functional, that here will involve some operator, for example, the gradient acting on the image. And we want to make a reconstruction here that has a relatively low gradient energy, so it will promote smoothness. So now if you just do the math, because this is quadratic, so you can crank out the closed form here. And what's interesting with this closed form, so what you see here, you have a transpose of the imaging operator that usually in jargon in imaging we call back projection. And then you have this correction here, and that if we call that filtering, you have the famous filtered back projection algorithm. Now, what we can do also, we can be more general, using other norms than the 2 norm. And here, so this is a general formulation here, where, for example, to this output of the operator, pixel-wise, we may apply, let's say, a power of p to get a p norm. And in that case, actually, you can design relatively easily a steepest descent algorithm whose form is here. And actually, we will see that this algorithm, in fact, has a form of a recurrent neural network, and that will also be used in the upcoming talk. Now, the story p equal 1, so L1 norm promotes sparsity, so that goes with compressed sensing. And so it's always the same problem here, except we've replaced the regularization by L1 norm, also acting on the L operator applied to the image. And then there's a very nice way of solving that problem that's based on forward-backward splitting. So essentially, you first concentrate on the data term, you do a gradient descent on the data term, and then you do a second step that will try to enforce this regularization. And this second step is embodied in a operator that we call the proximal operator, and the proximal operator is defined as a solution of that problem. Actually, if you look at this problem, it is in fact a denoising problem, because it's not the same as the reconstruction problem, but it would be a denoising with a regularization that's given by G. So if you have a good solution of that, then what you do, then you just repeat, and miracle, I mean, this converges, and you know, it's very much the basis for most work in compressed sensing. And now the proximal operator also, so I just told you, in fact, it is a kind of denoising. So this algorithm gives you an iteration between steepest descent and denoising with some good steps here, and this will converge to the solution of that algorithm, of that problem here. So this works pretty well, and here's an image out of our work, I mean, you know, like almost 15 years ago, where we were applying that to MRI. And so if you are undersampled in K-space, you get those kind of aliasing artifact. If you use L1, you can get much better reconstruction. And of course, I mean, this has had a huge impact in imaging, because those methods, they were pioneered by Lustig and Donoho in MRI, and then adapted by manufacturers of MRI, and also, I mean, virtually applied to any imaging modality in sight, leading to many publications, and that was the time of compressed sensing. Okay, but since then, things have changed, and the neural network have taken over. So let me just give you a little peek at neural network, again, seen through the lens of what was done in my lab. So we had a postdoc, who's now a professor in Korea, Jin Kyung, who actually proposed that we use deep neural networks to take a relatively poor reconstruction, let's say a filtered back projection reconstruction in the case of compressed sensing when we have poor data. And we train the neural network so to improve the quality of this not so good reconstruction. And he proposed doing that with UNet. And he had very nice results. And so here's just to show you a case of CT reconstruction where we reduced the number of views by 7. And so if you do a filtered back projection, so it's this L2 minimization, you get that kind of reconstruction. Here is the signal to noise ratio. If you use compressed sensing, you get this, okay, much better. But now if you use deep neural networks, wow, there was a jump that was almost equivalent from going to filtered back projection to compressed sensing, and then, for compressed sensing to deep neural network. And so that, was really fantastic. And we were lucky to be among the first to do that. And actually this earned us a Best Paper Award also in IEEE. And so this works, on different modalities. But of course, we were not the only ones. So many people had the same idea at the more or less same time. And then there was almost a replay of the story of compressed sensing. So everyone started applying a deep neural network and revisiting all the compressed sensing algorithms and modality, publishing lots of papers, often in very prestigious journals. And so there, the life was very nice because, okay, you could relatively easily get some good publications. Okay, but those times are over now because, it has been tried on almost any modality. But then people also realize, well, not everything is not so good maybe with those deep learning methods. So first of all, they require lots of training and lots of data. So that's not so good for the planet, as we know. They are hard to tune. And so it requires, experienced engineers, our graduate students. But what's more disturbing is actually they lack robustness. And that came really in the forefront in the 20s. So there's this very famous paper here, showing that actually those things are very unstable. And people also started reporting instances of hallucinations. And so, for example, here is an example of reconstruction so it was a study trying to reproduce some of those deep learning algorithms. And so that was data of a patient who had a tumor. So here, if you do a compressed sensing reconstruction, I guess it's a relatively good result. And then for that particular case, what was really very disturbing is actually the deep learning algorithm suppressed the tumor. Okay, so essentially not cured the patient, but if you show that to a radiologist, that's over. You will not trust your algorithm anymore. And so that is a case of reverse hallucination, okay, where you actually don't see the structure of interest. Okay, that got us a little back to the drawing board. So essentially, in what I told you, we have those variation methods. Now they're called handcrafted. They are based on math. They work, not as good as deep learning methods, but they have some advantages. At least they are safe. So the first advantage is they yield consistent reconstruction. So that just means if you take a reconstruction, put it you simulate the imaging, so then you will get something that is close to the data. But more important, the traditional methods are stable, under some condition. And so what do you mean by stability? So what you mean that if you have some measurements, y, and let's say you were to perturb a little your measurement, just tiny perturbation of the measurement, you don't want your reconstruction to change dramatically. And actually, this is not at all guaranteed when we use deep learning techniques. And that's actually the source of hallucination because you don't have this kind of stability constraint as here. But then, of course, there came hybrid approaches that kind of combine the two paradigms. And so the first approach here is a field of expert. And so here the idea was, okay, let's instead of using a TV regularization, let's try maybe to use something that is similar, but that would use filters that can be learned. And in fact, then if you look at the reconstruction, it has this kind of here just reconstruction of steepest descent. And in this case, since the filters are fixed, but if you just look at one iteration, I mean, this looks like a neural network. and since you're always using the same neural network, I mean, the same convolution filters, that's a recurrent neural network. And I mean, this can be refined a bit, and that we have done in our work by actually also learning the nonlinearities here. And that's also something that I'm going to discuss. And then there are also other approaches, very popular, plug and play, that just uses this idea of, you know, like iteration between steepest descent to enforce consistency and denoising. And so here the idea is to replace the proximal operator that would be specified by a G here, but by some kind of implicit denoiser that could be a neural network that is trained for denoising. This works quite well, but if you want to ensure consistency or some mathematical guarantees, you actually need here this proximal operator to be firmly non-expansive. And if you impose that constraint, actually it really limits very much the possibilities of this kind of algorithm. Okay, so now what we are going to look at is variationist approaches with learned regularizers. That's what's in the title. And the benefits here is that it's very easy to, I mean, just by design, it will impose consistency. It will be stable under suitable conditions, and it's also interpretable. And it's actually, you can have learning algorithms to, for example, learn the regularizers using unrolling or deep equilibrium. So they're very powerful tools to make that work. So now we're really like in the title was, you know, how do you design your regularizer? So first of all, we want the reconstruction problem to be well posed. And so let's say here we're in Switzerland, so cautious people, we want good quality. Let's start by saying, okay, we want convexity. I mean, this is what was in my title. And so that will ensure that everything works well. But now here is a second twist. Actually, what I didn't say here, that if you're learning a regularizer, I mean, this regularizer you could also use in the noise-free problem, okay, to solve that particular problem. Actually, the regularizer doesn't care about the problem you're solving, okay? It's supposed to inject prior knowledge. So let's look at the noise-free scenario just to design our regularizer. So one condition that we would like to impose, and that's not very standard, but it's absolutely, I mean, in some sense, crucial, obvious. Now, if you have no noise, now suppose you have a case where you get measurements that are twice the measurement of before. You really want your reconstruction to be twice the reconstruction you had before. So therefore, you want somehow to impose this condition here if you have no noise, okay, so that, you know, if you, okay, if you scale the data, you will scale also the reconstruction correspondingly. And now it turns out that this can be achieved if somehow you can pull out the scaling out of the regularizer. And so that's the condition that's given here. So you have a regularizer, you need to be able to pull out the scaling, otherwise you will not be able to do that. Okay, you can pull it out, not necessarily linearly. I mean, it can be some arbitrary non-linear function of alpha, but you need to be able to pull it out. And actually, this will be the principle that is based for the whole talk that's following. So now, what we want to design a convex regularizer, And we want a regularizer that satisfies the condition that I just gave you, that's called amplitude equivariance. And so now I'm just recalling some properties maybe from math here. X can be any Banach space, but in our case it's Rn. So you all know what's symmetry. So usually regularizers are symmetric. So if you negate the image, you get the same regularizer. You want convexity, that's very standard. Now, maybe you want homogeneity. Like, for example, if you can pull out a scaling factor, and so here you would get alpha to the power gamma. That's called alpha order homogeneity. And what I just introduced to you, amplitude equivariance. So it's a little more general in principle than homogeneity, because here it doesn't tell us, you know, what kind of nonlinear function we have here. So now here comes the first theorem. And now if we want a regularizer that's convex, so we all agree that's nice. Symmetric, we all do that. And then the new thing is equivariance. Then actually, this is equivalent to actually the regularizer being alpha homogeneous. It must satisfy this property, otherwise it doesn't work. And moreover, it means also that the regularizer we can express as a power of a semi-norm. And now if we want to be completely safe, because we may have problems with semi-norms because they have null space, so actually the regularizer should be a power of a norm. Okay, I didn't tell you which one. Actually, that's what we're going to learn. Now, how can you characterize regularizers that are arbitrary norms? Okay, so that's essentially what I want to do in what follows. So if you have any norm, a norm, what you can do, you can compute what's called the unit ball. So if we go like in space here, the unit ball is the locus of all the points that have a norm that's greater, smaller or equal to 1. And in fact, this is called a disk. Usually the unit ball will be center symmetric, convex, because all norms are convex. And to have a norm, also it needs to be absorbing. That means that somehow this unit ball, if you inflate it, you can capture every point in space. And then there's also a mechanism. If you know the unit ball, you would like to be able to design to recover the norm. And this is called the Minkowski functional. And so if you have a unit ball, the Minkowski functional will implement the norm that goes with that unit ball. So a unit ball is a convex set. So essentially what you do, you inflate the unit ball until you touch your point. And so the minimum inflation here, lambda, will give you the norm. And then there's a very nice theorem, classic theorem in functional analysis. So it tells you, if you have a absorbing disk, okay, so, you know, like that has those very relatively weak properties here. If you do the Minkowski functional, it will necessarily give you a semi-norm. Now, if your convex set is bounded, you know, and center symmetric, then actually the Minkowski functional will necessarily give you a norm. And conversely, if you have a norm, actually, then the unit ball will always be you know, absorbing disk, like I said here, and actually the norm will coincide with the Minkowski functional of the unit disk, of the unit ball. Okay, so this is interesting because it makes a connection between convex sets and norms. Okay, now here's the idea for what we're going to do. Now, essentially, we're searching for a regularizer that should be a norm, but we don't know which one. And the only thing we know, okay, a norm has a unit ball, and the unit ball should be a bounded absorbing disk. But now, here's the idea. If you have a convex set, like here, any convex set can be approximated to arbitrary precision by using polytopes. okay, like here. Okay, so if you put enough of those corners here, you will be able to approximate any convex set, and you know, by generalization, you will be able actually to represent any norm. And the other thing also that's important, if you have two different norms and you look at their unit balls, and if the unit balls are the same, you can say the norms are the same. Okay, so here is the idea. So we will consider convex polytopes, like here. And now a convex polytope is characterized by its corners, and so mathematically those are called extreme points of this convex set. And if you have those extreme points, if you take the convex hull of the extreme points, you are able to regenerate here the polytope. But there's also an equivalent way to represent polytopes, not by taking the extreme points, but by actually looking at the supporting hyperplanes. So think of facets, okay, and you put hyperplanes, supporting hyperplanes that will actually divide the space in half spaces. And if you take the intersection of all those half spaces, you're also able to regenerate your convex polytope. And once you have a convex polytope that is absorbing disk, then you can actually generate the norm by taking the Minkowski functional. Okay, so now what we want to do is to actually characterize all possible norms whose unit balls are polytopes. And actually we call those Banach spaces polyhedral Banach spaces. And what are those Banach spaces? It just means that the unit balls have a finite number of extreme points, which are those corners of or vertices of the polytopes. And so in that case, okay, if you know the vertices of the polytope, if you take the convex hull, you generate the unit ball. If you take the Minkowski functional, you have the norm. Alternatively, I told you there was another representation using the supporting hyperplanes. And so it's an intersection of half spaces. And so again, here you can generate the unit ball. You do the Minkowski functional, you get the norm. Now it gets more interesting. Okay, this is a bit abstract, but now if we want to relate that to signal processing, now if you knew the normals of the supporting hyperplanes, those are F, so those are vectors, then actually you can express this norm as a L infinite norm, you know, of some operator that's applied to X. Okay, so that would be like a regularization operator. Okay, so you can shape more or less your unit ball by choosing different normals here. Okay, so that shows that somehow there's a connection with L infinite norm, and maybe you prefer L1 norms, and so maybe this is the more interesting one. Now, if you knew the vertices of your polytope, now you have this norm here. So this should remind you of compressed sensing, because essentially we use the vertices as a dictionary. So we are trying to represent the vector X in the dictionary, and we're looking for the code word that is the sparsest. And the L1 norm of that code word gives us exactly this norm here that would be associated to that. And I mean, this is kind of new. At least it was not formulated in this way. So, and this will make a connection with compressed sensing, okay? Because, and the design of arbitrary norms. So if I want to summarize the situation here, so if we have a unit ball, there are two ways actually to describing unit balls, either by giving the vertices, and so those are these yellow vectors, and this somehow will go with the L1 norm. That is, of course, in the dictionary. So the dictionary will specify the vertices, or alternatively, we can use the facet vector. So it's the normals of the supporting hyperplanes. And now if we go with the facet representation, then we have some connection with L infinity norm. And actually this suggests a parametrization of polyhedral norms. So essentially, if you look at the following scheme here. Now let's just create a rectangular matrix that has a number of vectors here and a greater number of vectors than the ambient dimension D. Then either you can look at it like that and define a kind of L1 norm, so that will define the polyhedral norm, or you can use this dictionary here rather as the transpose as a regularization operator and apply L infinite norm. And actually this theorem tells us that those two things actually are the dual of each other. And so they generate a dual pair of polyhedral Banach spaces. And so what this means, actually the geometry of those unit balls is completely determined by the extreme points of this dictionary here. And so those actually describe all the geometry of our norm. And so what's interesting here, so if you have a dictionary, so this theorem already tells you that you don't need to take every one in the dictionary. You just need to consider the convex hull of the dictionary element, and then you just look at the extreme points, and that's the cleaned up dictionary. So for example, if we started with a dictionary like that, so we want to determine the extreme points, and so in some sense clean up the dictionary. What we first do, we symmetrize the thing, okay, because we are having plus and minus, because we have the symmetry of norm. And then we only keep the ones that are corners. Okay, and that will actually give us the representation that is exactly encodes for the vertices of our unit ball. And here is actually what as described in the title. I'm claiming I have a universal parametrization of convex amplitude equivariant regularizer. Okay, so I can start from any norm. Okay, so that's the norm I would like to learn. Then for any norm, I can have a certain epsilon that tells me how close I want to be. Then there exists actually a number of supporting hyperplanes or vertices such that this norm I can approximate arbitrarily well by this L infinite norm, okay, with a certain regularization operator. Maybe you don't like L infinite norm, so there's the dual version. This norm I can approximate arbitrarily well by choosing a large enough dictionary and using the norm associated with the dictionary, like that is given here. And so this is universal, so it will allow me to encode every convex regularizer. Okay, so which is kind of nice. Okay, so at least now we know that, in fact, what we were doing in compressed sensing, if you make a dictionary large enough, in principle, we can encode any possible convex regularizer. But now let's try to implement that. So first of all, the regularization norm is given by this, okay? But it can be merged into the problem, and then you recognize your classical compressed sensing problem where you have a dictionary G and you're looking here, you're trying to optimize getting the sparsest representation. And so you're extremely happy because this is what we have been doing for 10 years. So this in principle we know how to solve. Now there's a problem though. It's very easy if you know the dictionary, but it's actually very hard to learn the dictionary. And here Stan. Who is Stan? Stan is one of my PhD students, extremely good with machine learning, and he has been trying very hard to learn in that scenario, and it doesn't work well. And there's a reason, because in fact this thing has a huge null space, so it's very, very badly ill-posed, and it's very hard to learn. Okay, so we say, okay, forget about L1, so let's go to L infinity. This looks very classical, except here we have a L infinite norm instead of L1, but our theorem tells us this is universal, so why not? And now let's try to learn here. So it's elegant, but now Stan again, the concrete guy, it tells me, yeah, that looks nice on paper, but if you do back propagation with this kind of setting here, because you have the L infinite norm, actually when you will back propagate, it will only sort of back propagate on the guys that are active, and so that will be very, very slow to converge. Okay, so we are now here in a case where we have a nice theory, but we don't really know how to train. And so here is a solution. and the solution, maybe go back to the initial form. Okay, the initial form, we had here our inverse problem. Here with this is the so-called analysis version, where we have a regularization operator in handcrafted framework. This is for example TV, and now maybe we want, instead of TV, we want to put a neural network here and learn L. So first of thing we can say, yeah, okay, if you do that, actually this will generate a polyhedral norm. So we're exactly in the framework. But we want to relate that with the other synthesis scenario. And so this is what I call analysis by synthesis. So, okay, so if you apply L to some signal S, you get Z. But now if actually here we had the condition that this will be a norm if and only if rank of L is D. But if rank of L is D, then in fact you can invert L, but taking a generalized inverse. And then you can find actually a dictionary G tilde such that this holds. So we essentially have a way to invert the regularization, but we're in a much higher dimension. Okay, so then we can actually rewrite the problem like that. And so here it looks very much like a compressed sensing problem. There's just a little difference here that we're not allowing for every Z. We're just only allowing those that are in the range of the regularization operator. And because we don't like constraint problems, we can reformulate it like this. And here we're just doing like compressed sensing by putting an indicator function here that will force actually the solution to be in the range of the operator L. And okay, now let's transform that in a machine learning friendly parametrization. Now, because here we need to invert L, in general, this is a little complicated, and therefore we will focus on what we call tight frames. And tight frames are very easy to invert because you essentially only have to do the transpose. I mean, tight frame is not a square matrix, okay? It is a rectangular matrix, but that's extremely easy to invert. And so then we're using a singular value type representation where we are putting still diagonal elements, which are just weightings, and then a filter bank here that we call a Parseval filter bank because it's very easy to invert. And so that then gives us the form of the problem that we will use for implementation. Okay, now what we have here is a tight frame that will be parametrized. In practice, it will be parametrized by some ortho transformation. And then we want to solve that problem. And so this is just the standard stuff. Here, this is the sort of sparsity constraint, but here we will be a little more general. here we will allow for other things than L1 norm, actually any convex potential. So it could also be L infinite norm, or no, not L infinite, LP norms or whatever. And this is the condition that forces us to be in the range of the regularization operator. And actually to enforce this condition, it's very important to have a projector on the range. And if it's the tight frame, it's almost trivial. You just apply this operator and it will project you in the required range. And now to solve that problem, we have essentially two algorithms. The first one, which is a proximal operator, for example, if you have a L1 norm, because it's not differentiable, so we will use proximals. And so now the only condition here is that we know the proximal of the pointwise potential. And so, for example, if it's L1, it's very easy because it's a soft threshold. And so here's the algorithm. So essentially we do steepest descent on the data term, your prox. Okay, so that's a standard algorithm of compressed sensing. But here what you do, you project onto the range of the operator and you iterate. And this will converge. Okay, this is when you're non-smooth, but if your potential is smooth, differentiable, you have something even simpler. You can just do project a steepest descent. So where the steepest descent on this thing here without I mean this projection constraint, and then you apply a projection to put us back in the feasibility set, and this will converge. Okay, so let's describe some implementation of that. So how do we deploy those convex regularizers? So we will train them on denoising, and this is very easy, and we will take natural images, put more or less noise. And what is the architecture of the regularization network? We will use here n-square channel Parseval filter bank, and this is very nice because such a filter bank is just parameterized by an orthomatrix. Okay, so somehow the impulse responses have to be orthogonal. And so that's relatively easy to impose, for example, in PyTorch. And then you have adjustable nonlinearities per channel. We have this multiplication factor that comes from the SVD decomposition. And in our theory here, we just need to put L1 regularization. But then we will compare with more general schemes. For example, in this scheme, we will actually train a potential to be a free-form spline, but subject to convexity constraints. And that we can do in the two algorithms, because we had one proximal algorithm and the other was a steepest descent. And so there we can also eventually learn the nonlinearity. So this is the theory, and here this is just maybe to try to do more general. And now, how do you train the nonlinearities? We have a spline toolbox. So it's not so much emphasized in this talk, but it is actually a Qt framework that allows you to train nonlinearities. Okay, and so then we are going to apply that to compressed sensing MRI. So here are the denoising results. And so we used either this, okay, so this is the sort of regularizer predicted by the theory, and this is a more general form where the potential can be learned. And so here are the results. So if you learn this using the gradient algorithm, you get this kind of results. If you learn this using the proximal algorithm, you get this kind of results. And now if you don't learn this, but just use weighted L1 norm as predicted by the theory, you get this. And now what's remarkable is that actually the nonlinearity predicted by the theory is actually almost equivalent to the learned one if we didn't have the theory. And it's even better than the one that's learned by a gradient. And maybe the reason there is because if for some reason the optimal nonlinearity would be L1, gradient has very hard time to learn L1 because you know it is non-smooth. and so those things are almost identical. And actually, if we look at the learned nonlinearity, so that is for this algorithm here, we were very nicely surprised that it actually exactly learned the soft threshold. So which is very reassuring. It confirms that our theory, in fact, is exactly on target, because we predicted that the L1 would be universal. Now we also did some robustness analysis of the denoising. And essentially here is the regularization. So what we have in principle, okay, we have to adjust this, and then we still have a lambda parameter. And in fact, once it's trained, the only thing you can adjust is lambda, okay? You're not allowed to adjust the filters again. So now what we tried, actually different levels of noise, and now we retrained here for every level of noise, which in fact you're not supposed to do, but this will for sure give you the best results. And now if we only train on the middle here, and we just deploy this solution to the other noise level, we get very competitive results. And now if we now jointly train on all noise levels, you know, we also get more or less the same result. So actually what that illustrates is that our scheme is very robust. Okay, you can essentially train on one noise level, and for the lambda here we've even trained a neural network that predict the lambda that goes with the sigma. Okay, let's apply that to compressed sensing. And so here are the results. Again, here are those three algorithms. So the one where we learn the nonlinearity also, and the one where we use the weighted L1. And what we see here, that actually we are essentially as good as when we don't have this theoretical knowledge and we still have to learn the nonlinearity. And so we have something relatively robust that exactly fits compressed sensing, except that the dictionary now is being learned. And of course, we outperform compressed sensing. And so here are some results. And so you see that essentially those three reconstructions are essentially undistinguishable, and that we improve upon a classical algorithm. And so that essentially gets me to the end here. So we were faced with this problem here that, classical stuff works well, but not so well, but is safe. If we do deep learning, okay, sometimes, most of the time we will get very good result, but sometimes, I mean, it just doesn't work. And now somehow here we are, if we compare with other schemes like plug and play field of experts, here we are in the same ballpark, but now the advantage that we have, that because there's L1 in the background, we have guarantee of consistency, robustness, stability under suitable conditions. So essentially we have the same math as we had with compressed sensing, because once you have learned, in fact, you are in the scenario of compressed sensing. Okay, conclusion. So this is a kind of joke. I call it Return of the Spline, episode 67, season 4. And you will wonder, hey, Unser is completely crazy. He sees splines everywhere. I mean, there were no spline in this talk. Huh? Did I talk about splines? Yeah, a little, just before. So where are the splines? Well, actually, it's full of splines, my talk. Polyhedral representation. A unit ball, when you represent it by a polytope, you are doing a spline approximation of the unit ball. Okay, so there's still spline in the background. And now if you look at the reconstruction algorithm itself, now it is a recurrent neural network that is results from the composition of linear maps, which are the filters, and continuous piecewise linear nonlinearities. And this composition actually preserves that property. So it means that at the end of the day, the reconstruction algorithm that we engineered is a spline, okay, but the spline in very high dimension, and the spline that we had to learn by learning the dictionary. Okay, so this gets me now really to the end. Here are the references. So we had some precursors of this, but then we have the enabling tool, which are those Parseval convolution neural networks. So those are those kind of ortho filter banks that will make life much easier. I mean, they're really easy to train. And also the control nonlinearity that I used in the competing algorithm. And if you want all the details, there's a fresh manuscript that has been accepted for SIAM Journal of Imaging Sciences, and it's also available on arXiv. And finally here, I really have to thank the important guy here, who is Stan, who did, all the implementation, and many other people that had been kind of involved in the work that has been done over the years, and also the funding, ERC, that has funded this research. So thank you very much, and I'm open to questions.